At 5:49 in the morning on August 23, 1991, a sound like a gunshot cracked through the base of a 16,000 square meter concrete structure floating in a Norwegian fjord. Within minutes, seawater was flooding in at 1,000 tons per minute, and 22 workers had 18 minutes to get off. The structure was worth $700 million. It sank because of one number in a computer model. Sleipner A was a gravity-basis structure, a GBS, for the Sleipner East gas field in the North Sea, built for Statoil by Norwegian contractors using the Con-Deep system, concrete deep water. The concept was extraordinary. You build a massive concrete hull in a sheltered fjord, float it out to sea, then sink it onto the seabed by flooding its cells with ballast water. The platform deck sits on top, 60 meters above the waves. The base of Sleipner A consisted of 24 cylindrical concrete cells, each 12 meters in diameter, designed to hold ballast, store crude oil, and carry the 57,000-ton deck above. But to understand what went wrong, you need to know about the part that connected them. And that would have been bad enough, except almost nobody was paying attention to it. Between every pair of adjacent cylinders sat a triangular section of concrete wall called a tricell. Think of it like the webbing between your fingers, not the main structure, but the thing that transfers force from one finger to the next. The tricell walls handled shear forces, the lateral loads that the sea and the ballast pushed between neighboring cells. They were critical. But they were also small, geometrically awkward, and easy to overlook. The engineering firm responsible for structural analysis, A.C. Olsen, later Over Arup and Partners Norway, used a finite element program called Nastran to model the entire base structure. Finite element analysis, FEA, works by breaking a complex shape into thousands of tiny elements, calculating forces on each one, then assembling the results into a picture of how the whole structure behaves under load. The quality of that picture depends entirely on one thing: how fine you draw the mesh. Too coarse, and you miss what matters. Too fine, and the computer runs out of time. The engineers chose a mesh. The mesh was too coarse. Here is where a small decision becomes a $700 million mistake. The tricell walls were not rectangular. They had skewed, curved faces, geometry that doesn't fit neatly into the grid-like elements that FEA programs use. When the mesh is coarse and the geometry is complex, the software has to interpolate, essentially guess, the stresses at points between the element nodes. In this case, the interpolation underestimated the shear stresses in the tricell walls by 47%. Not a rounding error, not a marginal uncertainty. Nearly half the actual force was invisible to the model. The engineers looked at the output and saw a structure that could handle the loads. They designed the reinforcement accordingly. The tricell walls were made too thin, too little steel, too little concrete. And here's the part that turns an error into a disaster. Nobody ran an independent check, no second model, no mesh convergence study, the standard practice of refining the mesh until the answer stops changing. One model, one mesh, one number. The design moved forward. By August 1991, the GBS was complete and floating in Gansfjord, just outside Stavanger. The next step was a controlled ballasting operation, deliberately flooding the cells to sink the structure to a depth where the platform deck could be mated on top. As the water level inside the cells rose, so did the hydrostatic pressure on the tricell walls. This was exactly the load the walls were designed for, or rather, the load the computer said they were designed for. In reality, they were carrying almost twice the shear stress the model predicted. At 65 meters depth, the first tricell wall failed. The engineers knew something was wrong. What they didn't know was that the failure had been locked into the design 3 years earlier, the moment someone accepted the Nastran output without refining the mesh. At 5:49 a.m., a loud crack echoed through the concrete base. A tricell wall had split open, and North Sea water began flooding through the breach at a rate the ballast pumps couldn't match. 1,000 tons per minute pouring into a structure that weighed 65,000 tons. The 22 workers aboard felt the platform lurch. They evacuated in 18 minutes. Every one of them made it off alive. The GBS did not. It continued sinking, accelerating as it took on water until it struck the seabed at 200 meters depth. The impact was so violent that the concrete base imploded. The shockwave registered as a magnitude 3.0 seismic event. Nearby tugs lost sight of each other in the spray. $700 million of concrete and steel, gone in minutes. The most expensive structure Statoil had ever built, destroyed before it ever produced a cubic meter of gas. Statoil commissioned SINTEF, Norway's largest independent research institute, to investigate. The team produced 16 separate reports. Their conclusion was devastating in its clarity. When investigators rebuilt the finite element model with a properly refined mesh, the corrected analysis predicted that the tricell walls would fail at 62 meters depth. The actual failure had occurred at 65 meters, a 3-meter margin, eerily close. The refined model matched reality almost exactly. The original model hadn't come close. The 47% error was not a freak accident of software. It was a predictable consequence of insufficient mesh density applied to non-rectangular geometry. A failure mode that any mesh convergence study would have caught. The check that wasn't run would have saved $700 million. The platform was redesigned from scratch. A new GBS was built, this time with verified models and independent structural review. Sleipner A went into service on October 1, 1993, ahead of schedule. It operates to this day. The accident triggered an industry-wide overhaul. Mandatory mesh convergence checks and independent peer review of finite element analyses became standard practice in offshore construction. The case entered engineering curricula worldwide, a canonical example of what happens when you trust the output of a model without questioning the model itself. The Sleipner A collapse is sometimes called one of the most expensive software bugs in history. But that framing misses the point. Nastran didn't fail. The software did exactly what it was told to do. It solved the equations for the mesh it was given. The failure was human. Someone chose a mesh that was too coarse, and no one checked whether a finer mesh would give a different answer. The lesson isn't about computers. It's about the moment you stop asking whether the model is right and start assuming it is.